Hey everyone, welcome to lesson number 8. So we're going to be looking at transformations of trig functions, part 2. Today we're going to be focusing on changing parameters c and d. And so in the last lesson we were looking at changing the parameters a and b. So what impact that had on our amplitude and our period. So we're going to look at this example here, example number 1. Describe how the graph of the given functions compare to the graph of y equals sine x, where x is in degrees. So these transformations that are going to be taking place are exactly like the transformations that you would have seen with just transformations of functions in Unit 1, Lesson 1 to 5. Right? So in this case, my x values are being mapped to x minus 30 degrees, and so this is going to result in a horizontal translation, and this is going to be 30 degrees to the right. So notice how it was minus 30. If it's plus 30, it's going to be the opposite. And if it was plus 30, it would have been 30 degrees to the left. If I have sine x plus 2, then remember I need to get, because this positive 2 is not in brackets with the x, I have to bring this positive to the other side in order to map it. So this would be y is mapped to y minus 2, which would result in a vertical translation. Excuse me. A vertical translation, and this is 2 units up. Next, I have two things happening. I have my x values being mapped to x plus 60 degrees, and I have my y values being mapped to y plus 1 if I bring that one to the other side. So I'm going to have a horizontal translation, 60 degrees to the left, and I'm going to have a vertical translation, 1 unit down. And if I look at what's happening in this last parts, I have my x values that are being mapped to x minus 45 degrees, and my y values being mapped to y minus 45. I don't have to switch it because it's already on my y side. So I'm going to have a horizontal translation, a horizontal translation, 45 degrees to the right. And I'm going to have a vertical translation, 45 units up. Alright, so in trig, this is something that's new. In trig, a horizontal translation is called a horizontal phase shift, and a vertical translation is called a vertical displacement. The reason why is because if you look at the graphs of cosine ratios, sine ratios, tan ratios, they act like waves, right? And so if we think about how we use waves in physics, we use them as physical representations of sound or of light, or just to describe how like a slinky moves, right? And then we talk about those things in terms of their velocity and their displacements. Class example number 2, horizontal phase shift. So we're looking at the horizontal translation and the vertical displacement, or the vertical translation. And if we're comparing it to y equals sine x, then remember that there's not going to be any phase shift or displacement in this original graph. However, if I look at y equals sine x minus pi over 4, this is going to be pi over 4 radians and to the right. The vertical displacement, there's no d value, no d parameter that is being implemented into this graph, so the vertical displacement is 0. And if I look at this next example, there's no horizontal phase shift, so that's 0. Nothing acting on the x, but I have this 5 that if I take to the other side and map to y, this would be 5 units up. In this example, I have 3 pi over 2 rads to the left, and on this side I have pi units down. Here I have C rads, and that's right, and I have D units up. Here I have C rads right again, and again I have D units up. All right, I encourage you to read this section on the next page by yourself. It's talking about what specifically is happening when you change the parameters C and D on the graphs of your sine or cosine ratios in the form of A cosine bx minus C plus D, where we know that A is my amplitude, B is the value of the period, C and D are my horizontal phase shifts and my vertical displacements. And it gives you all the information of how you specifically find each one and what happens with those parameters when you change them. But let's look at this next example. Class example number three. Consider equations of the form y equals a sine bx minus c plus d, and cosine where a is equal to 1, so my amplitude is equal to 1, the value of my period is equal to 1, and write the equation which represents a cosine function having a horizontal phase shift of 75 degrees to the right. All right, so a cosine function having a horizontal phase shift of 75 degrees to the right, which means that I'm going to have to start with y is equal to cosine. Now, I have an amplitude of 1 and a b value of 1, so I don't have to input those because the value is 1, so they're already inputted. So x minus 75 degrees, it's minus 75 degrees because we're going to the right. A sine function having a horizontal phase shift of 3 pi 5 over 5 radians left, and a vertical displacement 4 units up. So we're looking at the sine function this time, and we still have an amplitude of 1 and a b value also 1, so my period's also 1. If we're going to the left this time, then this is going to be x plus 3 pi over 5, and I have 4 units up, so that's going to be plus 4. I'll do this example. This one I think you guys could probably figure out once I do this one. This one, just because we're dealing with fractions, may be a little more confusing. All right, so find the amplitude. So we need to find A, we need to find B, we need to find C, and we need to find D of the graphs of the following functions defined on x as an element of real numbers. Okay, so I have my amplitude here. A is equal to negative 2/3. I have my b value right here. So my b value is equal to 1/4. So if I have my b value, that, remember, just because I have my b value doesn't give me my period per se. I have to find out what the actual period is still, and I do that by dividing 2 pi by my b value. If I look at my horizontal phase shift, it is pi over 12, so my horizontal phase shift is pi over 12, and last I have my vertical displacement, which is equal to 3. All right, now let's talk about this in the actual units. My amplitude is equal to negative 2/3 of a unit. My period is equal to 2 pi divided by 1/4. This, is equal to 2 pi over 1 times 4 over 1, or 8 pi radians. And here I should be putting squares around these. My horizontal phase shift is pi over 12. And let's be specific here, but that's rads to the right, or radians to the right. And lastly, I have my vertical displacement, which is 3 units up. All right. Next, we have basically the exact same question. We're looking for the amplitude, the period horizontal phase shift, and vertical displacements of the graphs below. Again, I'm just going to do this one here, B, because that's probably one that's a little more challenging. But if we look at this example, even if we look at this previous example over here, notice how notice what's going on with my x value. And so my x value has a coefficient in front of it, in which case I'm going to have to get rid of that coefficient. So in order to do that, I'm going to rewrite this as, and I'm dividing, actually if you do it like that, it's confusing. I'm dividing everything in the brackets by 2. So I'm factoring that 2 outside of those brackets, which would leave me with x minus pi over 4 plus pi. So again, I took the 2 out. When I divide everything over here by 2, then I'm left with x minus pi over 4. Remember, I only divided everything in the brackets. So only factored the 2 out of the brackets. The amplitude then is -1. It's negative cosine. My b value is 2. So that's going to tell me what my period is, remember. My horizontal phase shift is, or my c value is pi over 4, not pi over 2. I'm looking at this one now. And my displacement, my vertical displacement is pi. So amplitude is equal to 1 units. My period is equal to 2 pi over 2, or just pi radians. My horizontal phase shift is equal to pi over 4 rads to the right because it's negative, and my vertical displacement is equal to pi units up again. All right, so these are the answers that we would be looking for here. Compare the answer to class example number 4 and class example number 5. And so if we look at class example number 4 and class example number 5. All right. Sorry, I got a phone call through there. But let me just explain to you what I was talking about in this section. So the graphs from A to D, I'm just going to cover A and B because C and D are exactly the same, but represent the trig function. They all represent the same trig function. Write the equation of the graph in the form y equals a sine x minus c if a is greater than 0 and there's a minimum possible horizontal phase shift. So what we're looking at is if the original graph, in this case, is sine whatever the amplitude is here. So my amplitude, I know if I start from any points, any midpoint on this function and go from the max or to the min, it's halfway through there. So my amplitude is 4. And in this case, my amplitude is greater than 0 because we could say the amplitude is -4 too, but we're told that the amplitude is greater than 0 here. So my amplitude is +4 units. But what we're looking for is the minimum amount that this graph would have shifted. Right? Because it's a periodic function and it's repeated every period, that means that we could move it technically an infinite number of units over, but we're looking for the minimum amount that we would have moved it. So here I've mapped my original sine function, or my y equals 4 sine x, and if we look at where my new graph is, and this is the bolded one, the one that you have in your book, this new graph goes over to the right. So we know it's got to be a horizontal frame shift or horizontal translation to the right. Now the next thing to determine is what is the scale of this graph. So if I look at from 0 to pi, how many divisions there are between there? There's 1, 2, 3, 4, 5, 6 divisions. Right? So that means that this scale is broken into pi over 6. So each little division here represents 1/6 of this pi. So 1/6, 2/6, 3/6, or half a pi, 4/6, 5/6, and 6 over 6 pies, right? Which means that if I go from here to here, I've gone 1/6 and 2/6 over to the right. So 2 over 6 units is equal to 1/3 of a unit, which means that the amount I moved over, because what we're talking about is not 1, but it's actually 2 pi units and pi over 3 units, my minimum amount I would have moved is pi over 3, which means that I could then rewrite my function as y is equal to 4 sine x, and it's moved to the right, so that would be negative pi over 3. In this next example, this is where I got the call, is we're going the opposite direction, right? So again, my original function in this case is, if we read what my a value has to be, my amplitude has to be less than 0. So if amplitude is less than 0, then my a is equal to -4, right? So if a is equal to -4, then my original function would have been somewhere over here at pi over 2, and that's because a was negative. So that means that we were looking at the negative sign of x, which is why with this one above I drew it going up, but the original function has to be going down because it's negative. So it's just going the opposite direction. But now if you look at where my actual frame shift is, it's from this point to this point. And so again, if we have the same scale here, so every time we move over away from my origin, it's going pi over 6 units, or 1/6 of a pi. So let's see, I got 1, 2, 3, 4 over 6. So I have my horizontal translation is 4 over 6 pi, or 2 pi over 3 units. And sorry, I shouldn't say units, I should say radians, right? Rads. And this is going to be left because now it's going the opposite direction. So if I were to rewrite my equation, remember a is negative, it's -4 this time, sine x, but it's going to the left, so that's plus 2 pi over 3 radians. Yeah, so that's kind of a fun question. Those are cool to do. Let's look at this class example number 7. Consider the graph shown. If the graph represents a sine function where my amplitude is greater than 0, complete the table and write the equation represented by the graph. Alright, so this one, if we look at this graph, this one is probably going to look a little more confusing to you, because if you look at the halfway point, it's not going through 0. All the other graphs you've looked at to this point, the halfway point has gone through 0. And so in this example, we have to move my halfway point. And so if we look at, where it goes from 1 to -5, and so that's 6 units. And so if we look at for where 3 units would be, I have 1, 2, 3. This is my midpoint right here. Alright, so this is the midpoint, and this is where we would have to measure our amplitude from. And so if I'm measuring my amplitude from my midpoint, then my amplitude then is 1, 2, 3. 3 units. Another way we could do that is by choosing the maximum point and the minimum point, right? And then subtracting the min from the max and then dividing by 2, and you'll get the exact same answer of 2. Now we got to find the period. So in order to find the period, we're just looking for 2 points where we have a repeat in an action. So if I start up, so I go up, go down, back up, and I would have to repeat that action right at this point. So these are 2 good points in order to determine what our period is. But remember, you can use any 2 points to do that. Like I could use right here, and sometimes it's easier to do something like this because then we're right on pi. But I go up, and so let's see where this point is repeated. So and right here. And so my period here is going to be so from pi to here. So this is where I'm looking at. Would be 4 pi actually. Yeah, 4 pi. So my period would be 4 pi. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, or start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Another way we can look at that is 12 times pi over 3, which would be, oh, sorry, I should put that up here. 12 over pi over 3, which would equal 4 pi. All right, now if I look at the original graph of a sine function, and we've established that the amplitude is 3, so let's just go 3 sine x, and then we'll graph that. So if I look at, if this was my starting point, then I've actually moved over to the left, right? So if this was my midline, if I move this up, and then it would end up here, and then if I moved over, it would be right here at the origin. So I've moved it to the left. And so in this section, we're actually moving pi over 6. Or sorry, this is a different scale. So this is actually increasing by increments of 1/3. Right? The last one was increasing by increments of 1/6, but we're actually going by 1/3 now to over a pi. So we've actually gone pi over 3 rads, and this is left. So you should write the actual words. I don't have any room in my box anymore because of this silly mistake. But again, if I think about how many increments there are to pi, there's 1/3 of a pi, 2/3 of a pi, 3/3 of a pi. So because there's an increment of 3, we know that this scale increases by 1/3. Give me a pi over 3 going to the left. My vertical displacement, however, so again, if this should have been on the origin, then we've moved down 2 units. So we have -2 units for our vertical displacements. Now, if I were to input this into an equation of y is equal to a sine b of x minus c plus d, then y is going to equal to a sine pi over period is 4 pi. So my b value, that's what we got to determine here, is b value. So my b value is equal to 2 pi over 4 pi is equal to 1 over 2. So my b value is equal to 1 over 2. X minus c, so my c value was pi over 3. And that was to the left, so it's positive, plus d, which was -2 units. So this would be my final equation.